Someone showed me something recently, a small demonstration, a research agent, an artificial intelligence system being used to do what I spent my life doing. It was given a question about quantum field theory, and it worked. It queried databases, it pulled papers, it read abstracts, it cross-checked citations, it ranked sources by relevance, it synthesized a summary, it checked that summary against the original claims. It found a contradiction, it revised. It produced a final answer, all of it, automatically, in perhaps 40 seconds. I watched this and felt two things simultaneously. The first was something resembling admiration, because the process, the shape of the process, was recognizable to me. That is how science actually moves, tentatively, iteratively, always checking itself against reality. The second thing I felt was concern. Not the concern you might expect. I was not worried about machines replacing scientists. That question bores me. It always has. Capability without understanding is a parlor trick, not a replacement. What concerned me was something quieter, something almost nobody in the room seemed to notice. The 40 seconds. Everyone was impressed by the 40 seconds, the speed, the result, the elegance of the interface. Nobody asked what the 40 seconds cost. And I am a physicist. I cannot stop asking that question. Because in physics, nothing is free. Nothing floats. Nothing happens outside of matter, energy, and the rules that govern both. So let me tell you what actually happened in those 40 seconds. Not the output, not the answer, the physics. Because once you see it, truly see it, the conversation about artificial intelligence changes completely. The questions change. The risks change. What you should be paying attention to changes. Everyone thinks AI is just software. They are wrong, and I can show you exactly why. Let us follow the research agent. Not metaphorically, physically. The moment you submit a question, something begins. Not a thought, not magic, a physical cascade. And if you want to understand artificial intelligence, really understand it, you need to follow this cascade all the way down. Step 1. Your question is tokenized, broken into fragments of language that the system can process mathematically. Each fragment becomes a number. Each number enters a matrix operation. That matrix operation happens on a chip. That chip is switching transistors, billions of them, on and off, billions of times per second. Already we have left the world of software and entered the world of physics. Transistors switching generate heat. Heat must be managed, so the chip sits inside a cooling system. The cooling system consumes energy. The energy arrives through a power delivery system connected to a grid. The grid was built over decades and operates under strict thermodynamic constraints. All of this for step 1, before the agent has done anything useful. Now step 2, the agent decides it needs to search. It queries a database. That query travels through fiber-optic cable as pulses of light. It arrives at a server, a different physical machine, possibly in a different building, possibly in a different country. That server processes the query. Spinning memory reads data. More transistors switch, more heat, more cooling. The results return through fiber. More light pulses, more energy. Step 3. The agent reads what it finds. Each word it processes, each token it evaluates, requires another pass through matrix operations. The model weighs billions of parameters. Each weighting is a multiplication. Each multiplication is a physical act performed in matter by moving charges through circuits. Step 4. The agent finds something interesting and decides to cross-check it. So it searches again. Another round trip through fiber, another server, another physical machine activating on another continent. Step 5. Contradiction detected. The agent revises its working hypothesis. This is not a metaphorical revision. This is the model recomputing attention weights across a long context window. The longer the context, the more compute required. The more compute required, the more energy consumed. Step 6. Synthesis. The agent drafts an answer, token by token. Each token generated requires a forward pass through the entire model. Each forward pass is an industrial computation dressed in the close of a sentence. Step 7. Verification. The agent checks its own answer against its sources. Another set of passes, another round of matrix operations, another burst of switching transistors. 40 seconds. Now tell me, what did you think you were watching? Because what you were actually watching was a distributed industrial process, spanning multiple physical machines, multiple buildings, multiple power sources, cooling systems, fiber networks, memory hierarchies, all of it executing in coordinated sequence so that a research assistant could hand you a paragraph. The paragraph is not the product. The paragraph is the receipt. The product is the computation. And the computation is physical, every step of it. This is not a criticism of the technology. I am not making an argument against artificial intelligence. I spent my career arguing that the universe is stranger and richer than our intuitions suggest. I am not about to start dismissing things because they are complicated. I am making a much simpler point. You cannot understand something if you only look at its surface. And the surface of artificial intelligence, a clean interface, a fast answer, 40 elegant seconds, is hiding an enormous physical reality. Now I want to give you the physics, not the engineering, not the business case, the actual physics underlying what I just described. In 1961, and I say this with some satisfaction because I was not around to see it, but I would have found it delightful, a physicist named Rolf Landauer proved something fundamental. Information is not free. More precisely, certain computational operations have a minimum thermodynamic cost. Erasing a bit of information, just one binary digit, produces a minimum amount of heat. The number is almost incomprehensibly small, far too small to feel in any individual computation. But Landauer's insight was not about individual operations. It was about the principle. And the principle is this: computation is a physical process. It is not an abstract mathematical event floating somewhere outside of matter. It happens in matter. It rearranges matter. And when matter is rearranged in ways that are thermodynamically irreversible, heat is produced. You cannot think without spending energy. Not a human brain, not a silicon chip, not an artificial intelligence performing 40 steps of research in 40 seconds. Now here is where it gets interesting. The human brain is extraordinary. It consumes roughly 20 watts, about the power of a dim light bulb, and yet it performs operations of extraordinary complexity. Evolution had 4 billion years to optimize it. It is massively parallel. It runs on chemistry. It is perhaps the most efficient information processing system ever assembled. The artificial intelligence system I described earlier is not the human brain. It is a very different kind of machine, and it shows. A single generation of a response from a large language model requires orders of magnitude more energy than the equivalent cognitive act in a human brain. The gap is not close. We are not on the verge of matching biological efficiency. We are, in energy terms, still building with very large, very expensive stones. This is not a flaw to be ashamed of. Early aircraft were not as efficient as birds. Early engines were not as efficient as muscles. Technologies improve, but you cannot improve what you refuse to measure. And here is the thing about the research agent I described. It did not run once. It ran 7 steps, 7 distinct computational phases, each requiring its own energy expenditure, its own memory access, its own transmission across physical infrastructure. A single research query, 7 physical events. Now scale that. Imagine not one researcher using one agent once. Imagine millions of people using agents all day long. Agents that do not simply answer, agents that loop, that retry, that check, that revise, that call tools, that run subagents, that operate continuously as a layer underneath human work. Each loop is not one physical event. It is many, and many multiplied by millions, running continuously, adds up to something that thermodynamics is already noticing. Even if the interface remains perfectly calm, even if the answer arrives in 40 seconds, even if it all seems from the outside entirely weightless. I want to address something directly. When people hear that artificial intelligence consumes significant energy, they often respond with percentages. They say, data centers account for only a small fraction of global electricity use. They say, compared to other industries, this is manageable. They say, you are exaggerating. I have some experience with people who respond to uncomfortable physics with percentages. It does not end well for the percentages. Here is what the percentages miss. Electrical grids do not experience global, they experience locations. A grid is a physical network of generators, transformers, transmission lines, and substations, and every one of those components has real capacity limits. When demand rises faster than infrastructure can be upgraded, the constraint does not appear as a global statistic. It appears as a specific problem in a specific place, a region, a city, a substation, a transmission corridor. And artificial intelligence demand is not distributed evenly across the planet. It is concentrated. It clusters around fiber networks, cooling water sources, land availability, and favorable energy contracts, which means the local stress can be substantial even when the global percentage seems modest. This is one of the oldest mistakes in infrastructure thinking. You look at the average and forget about the distribution. But distributions are where the real constraints live. Now add the second dimension. The research agent I described, 7 steps, 40 seconds, is not the future of AI usage. It is the beginning. The industry is now building what it calls agentic systems, not models that answer a question once, systems that operate continuously, systems that monitor, retrieve, update, synthesize, route, summarize, and act. Not once on request, but persistently, as a layer underneath other systems. I find this genuinely interesting, by the way. The aspiration is remarkable, to create a kind of distributed cognitive infrastructure that runs underneath human work the way electrical infrastructure runs underneath physical work. But let us be precise about what this means physically. A model that answers once produces one burst of compute. An agent that operates continuously produces compute at a rate proportional to its activity. An agentic layer underneath an entire organization produces compute at the rate of that organization's workload. Multiply this by every industry that now wants the technology simultaneously. Law, finance, medicine, logistics, research, education, government, manufacturing, customer service, media, software development. This is not a niche technology anymore. It is becoming what I would call a new metabolic layer of civilization. A system that processes information the way a body processes food, continuously, at scale, in service of ongoing function. And metabolic systems have metabolic costs. The International Energy Agency has projected that global electricity demand from data centers could approach 1,000 terawatt-hours per year by the end of this decade. 1,000 terawatt-hours. That is not a laboratory number. That is a civilization number. That is the kind of number that changes what gets built, where it gets built, who pays for it, and who goes without something else as a result. And this brings me to the part of the conversation that almost never happens. The question of which uses are actually worth it. I want to introduce a phrase, thermodynamic debt. Every civilization makes a bargain with physics. You spend energy to create local order. You smelt iron into steel. You pump water uphill. You refrigerate food. You transmit information across oceans. You heat buildings in winter. You manufacture instruments of extraordinary precision. All of this is a bargain. You create order here by paying with energy and waste heat somewhere else. Physics permits this bargain. It does not forbid it, but it tracks it. Every joule is accounted for. Every calorie of useful work is matched by entropy somewhere in the system. Civilization, in a sense, is the art of making that bargain well. Spending energy on things that produce enough value, enough reduction in suffering, enough increase in capability, enough extension of human reach, to justify the thermodynamic cost. Now consider the research agent again. 7 steps, 40 seconds. A paragraph synthesizing a complex scientific question. Is that worth its thermodynamic debt? I would argue yes. Possibly enthusiastically yes. If a well-designed agent can accelerate scientific research, can help a human researcher navigate a literature that has grown faster than any individual can track, the value returned may substantially exceed the physical cost. But now consider a different use of the same technology. An agent deployed to generate marketing copy at scale. An agent used to produce summaries of documents that should not have existed in the first place. An agent running in a loop to answer questions that a well-designed database could answer instantly and cheaply. An agent performing $10 of infrastructure work to solve a 1-cent problem. These are not hypotheticals. These are current realities. And they matter because of a dynamic I watched play out once before in a different context. When a powerful technology arrives, the first instinct is not to ask whether each use justifies its cost. The first instinct is to use it everywhere, for everything, as quickly as possible, because the technology is exciting, because competitors are using it, because the interface is clean and the cost is invisible. The cost being invisible does not mean the cost is not real. I learned something important during the years I spent thinking about energy and matter. The universe is indifferent to your intentions. It does not reward enthusiasm. It does not grant exceptions for good reasons. It simply enforces its accounting. And the accounting here is becoming visible. Power has become a genuine bottleneck in the artificial intelligence race. Not branding, not cleverness, not the quality of the prompts. Power. Some of the largest technology companies on Earth are negotiating electricity contracts at scales measured in gigawatts. They are building their own energy infrastructure because existing grids cannot expand fast enough. A gigawatt is not a software word. It is a grid word, a utility word, a word that belongs in the same sentence as dams and power stations and transmission corridors. This is the conversation we are not having loudly enough. Not, what can the model do? But, what does it cost to do it? Who pays that cost? And does the value justify the expenditure? These are not anti-technology questions. I have never been anti-technology. I have been anti-sloppiness. And a civilization that builds a new metabolic layer on top of its infrastructure without asking what feeds that layer is being sloppy in a way that physics will eventually correct. The correction is rarely gentle. Let me return to where we began. The research agent, the 40 seconds, the paragraph. I told you I felt two things watching it. The first was admiration, and I meant it. The shape of that process, the iteration, the self-correction, the synthesis, is recognizable. It resembles, however imperfectly, the structure of genuine inquiry. And genuine inquiry is something I spent my life in love with. The second was concern. Now you know what the concern was. Not that the machine would replace the scientist, not that intelligence would become too powerful or too fast or too strange. Those concerns belong to a different conversation, one I find considerably less interesting than the one I have been making. The concern is simpler and older. It is the concern I felt every time a powerful idea entered the culture before the culture understood its physical consequences. People love the abstraction. They love the idea of unlimited clean energy, unlimited clean intelligence, unlimited clean anything. They love the surface because the surface is frictionless, and they are suspicious of anyone who points to the machinery underneath because the machinery is inconvenient and the abstraction is exciting. But I have spent considerable time with abstractions, and I can tell you from direct experience, the beautiful ones are always more interesting when you look at what is underneath them. E equals mc squared is beautiful, but what made it true was something harder and stranger and more demanding than the elegance of the equation. What made it true was matter and energy and the physical fabric of reality refusing to behave the way intuition expected. The interface of artificial intelligence is beautiful, but what makes it real, what makes it work, what gives it power, what makes it scale, is matter. Copper and silicon and glass fiber and coolant and electricity generated somewhere by burning something or splitting something or catching wind or light. That is not a complaint, that is the condition. And the mature response to a powerful technology is not to celebrate the surface indefinitely. It is to understand the condition. Build smaller when smaller works. Use agents where the outcome justifies the loop. Measure the thermodynamic debt of each deployment and ask honestly whether the value returned is worth it. Stop treating the interface as if it explains the system. A civilization that understands this can still build extraordinary things with artificial intelligence. Better science, better medicine, better tools for the researchers who come after me, better ways of navigating a world that has become, in many respects, too complex for any single mind. But it will build them honestly, not as mythology, as engineering, as thermodynamics, as a conscious bargain with physics, made with open eyes, not closed ones. The universe does not care about your utopias or your apocalypses. It cares about flows, balances, constraints. It always has, it always will. And when you understand that, truly understand it, you stop asking only what artificial intelligence can do. You start asking what it costs to do it. You start asking whether the bargain is a good one. You start asking the questions that determine whether a technology becomes civilization or merely spectacle. The interface is clean. The physics is not. And the physics, as always, is where the truth lives. Stay curious about the machinery behind the magic. That has always been where the real answers are.